So we will use the analogies from linear motion to describe our motion. If we know how the system is and its parameters at a given time, we can predict at a future time. So let's first look at our translational or linear motion and just remind ourselves about our three kinematic equations, which are here. V equals V0 plus AT. X, or we might have written this as delta x, which is displacement, equals V0t plus half AT squared. V0 squared equals, V squared equals V0 squared plus 2AX. These are our three fundamental kinematic equations. And up here, we just give essentially the definition of velocity, or distance equals velocity, average velocity times time. Yeah? The speed times time. Let's look at their equivalence. If you remember from the very first slide, we said equivalent to displacement is angular displacement in angular terms. So x becomes theta, okay? So I'm just gonna write here that our x goes to theta, our displacement is like theta. Our angular velocity omega has a correspondence with the linear velocity v, and our linear acceleration corresponds to angular acceleration alpha. Yeah? So everywhere that we have x in here, we are going to replace it by theta. So you see the first one becomes theta equals, we're going to replace the v by omega, so omega t. Let's look at the next one. Time remains the same. Yeah? There's no difference in time, whether you're going linearly or rotationally. So time doesn't change. Let's look at the next one. V equals V0 plus AT. This is going to become omega equals omega 0 plus alpha t. Yeah? We're just substituting exactly using this. X here, so theta, angular displacement equals omega 0 t plus half alpha t squared. You do need to be careful to keep the zeros when they're there, the subscript. That shows you the initial angular velocity. Huh? And this is the final one. Omega squared equals omega 0 squared plus 2 alpha theta, right? Alpha theta. So we are using analogies from the linear motion to describe the rotational motion. We haven't derived any of these equations, but these are all correct, and we are just going to use them. So that's what you need to do. You need to be able to use them correctly. Okay? So you do need to know these sets of equivalences. Okay? Let's go forward. So this is an analogy between linear and rotational motion. You need to know all of these formulae. Okay. And now we see the relationship between those linear quantities and their angular equivalents. Okay. So if our displacement, let's say we have an object which is rotating around in this counterclockwise direction, and the axis is perpendicular to the plane in which this is rotating. Okay. Then if you consider a point on the rim at some initial time, let's take it on the x-axis, so it's a distance r away, and at some later time, yeah, let's say this has traversed an arc whose length is given by s. Okay. So if s is this distance traveled, say arc length, it's equal to r times delta theta, right? Or sometimes we don't write the delta. Delta is a change in angle. Since our initial angle was 0, we just write it as theta. So S is equal to R times theta. This is relating effectively my linear or tangential displacement with my angular displacement, yeah, through this term R. So this is my linear displacement. Sometimes we wrote as X. Yeah? Here it's as RS because it's along the arc. Okay. Similarly, your linear and angular velocities or speeds, average speeds, are related by linear or tangential velocity equals R times omega. It's the same R. Similarly, angular acceleration okay, and linear acceleration. So this T is for translation or linear, okay. AT equals R alpha. So they're all related to their counterparts, angular parts, through this term R, yeah? So you need to know all these three relationships, very, very important, to be able to convert back and forth. Let's do a simple problem on this to use these equations. Suppose a teenager puts her bicycle on its back and starts the rear wheel spinning from rest to a final angular velocity of 250 RPM in 5 seconds. Okay, so if we want to write down the information that was given to us in this problem, what do we have to write? Rear wheel starts spinning from rest. That means my initial angular velocity was 0, yes? And it goes to a final angular velocity, omega, of 250 revolutions per minute. We want to be in radians per second, yeah? So we want to convert this 250 to radians. We know that this is 2 pi radians, yeah, in 1 revolution. So now we're in radians, but we're still per minute. We need to change the per minute to per seconds. So in a minute, there are 60 seconds, yeah? And now we are in radians per second, yeah? So you do need to do these kinds of conversions, very important. And how long does it take to change this angular velocity? It takes time of 5 seconds. Okay, let me just erase this S here. This is from the previous slide. So we want to calculate the angular acceleration. Angular acceleration is rate of change of omega with time. Yes? That means omega final, which is this value here, minus omega initial, which is this value here, which is 0, divided by 5 seconds. Yeah? So you would do all of this divided by 5 seconds, and you would get your result. We'll look at that in the next slide. All of this is part A. And what happens in part B? In part B, if she now slams on the brakes, causing an angular acceleration of negative 87.3 radians per second squared, how long does it take the wheel to stop? Okay. So this time we need to find T. We need to use essentially the same concept, except now our starting velocity is given because we just calculated that final angular velocity. That will be the starting one. And we have a constant angular acceleration of negative 87.3. Yeah. So we're going to use that value. And we're going to use omega final has to be 0 since it comes to a stop. Okay. And here our omega initial is this value here. Let me just change the color so it's a little more obvious. This value here is going to be my omega initial. Yeah? We're going to calculate that. And what we need to find is T or delta T, same thing. Okay? So let's look at the solution. You need to actually work this out, okay? And then go to the next slide and look at the solution. So here you're going to compare your answers with mine, okay? This is the first part. We find alpha, and this was the conversion that I did, yeah? And it comes out to be 5.24 radians per second squared. And then part B on the next slide, we're solving for time, and it comes out to be 0.3 seconds, yeah?